I want to give you a couple examples of continuity with piecewise functions. I think they're kind of the most interesting and probably the hardest ones to figure out the continuity for. So let's take a look. First example here. Well, we've got a polynomial. Those are always continuous. That's good. Cosine, that's just a big wavy thing, remember? That's continuous. So what's the big deal here? Well, we know that we're just taking a piece of this quadratic and a piece of that trigonometric function. And if those two pieces happen to match up perfectly, it won't be continuous. If they don't match up, then it won't be. So we have to look at that breakpoint. We have to look at that boundary line. So here's what I want to do. If you happen to know what these functions look like, well, that's great. Most of the time, you might have an idea. But do they match up? And sure enough, here they do. There is a solid dot on the purple graph, 2x squared plus 1, and an open circle for cosine. But you'll notice that it will go smoothly into the next one. There is not a gap, there is not a jump, there is nothing there that will make that discontinuous. But if you don't know what the graph looks like, take the limit of each of these. Take the limit as I get really close to 0 from the slightly negative side, from the left-hand side, and then take cosine's limit as I get really close to 0 coming from the right. If both of these happen to be the exact same number, that means they're going to meet at the same point. That boundary of 0 between those two is exactly the same, and therefore that example is continuous. Let's look at the next one. Find the limit of each of those functions as you approach 1. Now, the one that's less than 1, we're going to use a left-hand limit. And the one that's greater than or equal to 1, we'll use a right-hand limit. Once you discover those points, you'll find out that these two functions are definitely not going to be continuous. Look at it. One of them goes right up to -2. One of them starts at 3. You can always graph these. So if you have access to a graphing calculator or you just have a general idea of what these look like, it'd be great to use some rules for transformations. This one's 4 times taller and shifts down 2. This one, half as wide, and it's moving, 1/2 to the left. But basically the graphs will look something like this. So as you can see by the graphs, no, there's a big gap in there. That's a jump discontinuity. There's an essential break in there. You'd be going along like do. Oh, I have to jump way up here to continue with the graph. That's not continuous. So let's take a look at a couple more of these piecewise functions. In our next example, now we've got a 3-part piecewise function. And with that 3-part piecewise function, you've got 3 graphs. So now we've got 2 boundaries. We've got to check and see, hey, at -π/2, are these functions the same? And then we have to check and see at 3, are these functions the same? So either all these functions are all going to meet up nicely and it'll actually be continuous, or they'll all be different. Or could there be another option? Take a moment and check and see on your own what might happen. I hope you had a chance to figure this out. At the first boundary, just from the left-hand side, -π/2, that's going to be equal to -2. And then when I look at this function here, it's going to be equal to whatever -π - 1 is. Are those the same value? I don't think so. If the y-coordinates aren't the same, it's not continuous right there between those two. Meanwhile, for this next set, right around the point at 3, just to the left of 3, I'm using the middle function. Anything less than 3, 2.99 for instance, all that jazz. Anything a little to the right of 3, a little bit greater than, I'm using this rational function here, which both of them are 5. Wow, that means these two functions really are equal, and now we know where this function is continuous. It turns out that with only one discontinuity, there's only one place where it isn't continuous. This whole function up here, sine, is continuous all the way up to the end of its boundary, but then there's a break. And then from -π/2, these two do match up, so they're nice and even. Our final example is what happens when we say p is a continuous function. If it's continuous, what does that variable a have to equal? First, the limits are equal. Second, I find those limits. I plug in -2, and now I can solve. If p is continuous, a is -9.